Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone. So good morning, good afternoon, and welcome to this second part of the workshop we are organizing under the AI for Good umbrella, thanks to ITU and other organizations. In the workshop of today, we will see how to verify the deforestation in the Amazon, learning something that will be can be used by you everywhere, as a matter of fact, in the world. So please pay attention, because you will learn something that you will be able of reproducing also in other parts of the world where you are interested in analyzing this phenomenon of deforestation. First of all, I want to introduce the speaker with me today, who is Vasil Yordanov. Vasil is a research fellow at the Politecnico di Milano, and is also a PhD candidate, but mainly at Politecnico is a research fellow, and is the person who, as a matter of fact, prepared this workshop. So thank you so much, Vasil, for doing that.
Thank you, and hello everyone.
Okay,
welcome.
Thank you. And then we have some assistants today. And specifically, I'm very happy to introduce Juan Francisco Nieva.
Hello, everyone.
Hello, Juan Francisco. And Juan Francisco is a student at the Politecnico di Milano. He's a student of the Geoinformatics Engineering course. So thank you for being here and helping us with this workshop. Then I want to introduce Alessandro Austoni.
Hello, everyone. Really happy to give a little help to this project.
Thank you, Alessandro. Alessandro, again, another student of Geoinformatics Engineering at the Politecnico di Milano. And then Martina Esposito.
Hi, everyone. So glad to be here.
Thank you, Martina. Again, so all the students who are here as assistants are all students of the Geoinformatics Engineering at the Politecnico di Milano. So I won't repeat that anymore. But thank you for being here, helping with the questions and answers. Then we have Ahmed Abdelgadar.
Hello, everyone. I'm so happy to be here with you.
Hello, Ahmed. Thank you. Then we have again another lady, Giulia Leonardi.
Hello, everybody. Good afternoon. Very happy to be here.
Thank you, Giulia. And we are also happy because we see that there are also ladies doing that. So I'm very happy about that. And Mohammed.
Hello, everyone, and good afternoon.
Hello, Ahmed. Thank you for being here with us and helping us with the answer. And last but not least, Nicolina Zalemi. Nicolina, you are muted.
Can you hear me now?
Yes, yes.
Happy to be here again.
Thank you. Thank you so much. Thank you. Okay, thank you guys. So I believe that now it's time of starting. Are you ready?
Of course.
Fantastic.
Yes.
Fantastic. Let's go ahead. And go ahead means that we are organized in this way. I will start presenting step by step. And while I'm presenting, please pay attention to what I'm saying. You don't need to do what I'm saying. You need just to follow what I'm explaining, because then you will have a second replica of what I'm showing you with Vasil, and Vasil will show you practically how to do that. So in my opinion, the best is if you pay attention during my short presentation. I will present some slides, I will present some steps, then I will stop and give the word to Vasil, and Vasil will show you step by step what you have to do. Okay, so let us start recapping what we did last time in the part one. We selected one case study. The case study was one part in the Pará state of Brazil. And you see here, which is the part we are interested in. Here there is a detail. We selected one region where the deforestation was enough evident. And if we look into the detail, this is our area of interest, AOI. So the area of interest, which is around 50,000 square kilometers. And you see here the result that we get in the end of the classification of today. Okay, so the aim is to study the forest loss and gain in the period we are examining. Specifically, last time we deal with an introduction to Google Earth Engine, showing what we have to do, the main procedures, the main variables, the main functionalities. We started preparing the data, and today we will see the classification of our imagery, the evaluation of the model we are creating, and then we will compute the forest loss and forest gain. With respect to data preparation, just for recapping, I want to recall you that we defined the area of interest, we defined the cloud mask, because as we are dealing with multispectral images, obviously, if there are clouds, we have to remove the effect of clouds. Then we define two periods for our analysis. We defined which data we wanted to use, and we apply the filters to the data. Today, we will see, as we said, the classification, model evaluation, and forest loss, forest gain. Okay. So with respect, we are not going to repeat what we did the last time, but if you didn't attend last time, or if you don't have saved the code that we developed last time, you can click here on the PDF and obtaining the code from the part one. Okay, let us start now with the part number 2. And this is the situation. We ended exactly with this step. So we ended with showing you how it was possible to create this slide bar inside a Google Earth Engine in such a way to visualize on one side the oldest data, on one side the newest data. And as oldest data, we decided to consider Landsat 8. And specifically, what we did the last time was to create a cloud-free image corresponding to the month May, August 2015. And then, besides the bands already available, we decided to compute a new band that is the NDVI, and to consider this added level of our image that we will use for the classification. On the other side, we decided to consider the Sentinel-2. Sentinel-2 related to the period, same period, May, August, but in this case 2019. And again, we computed also in this case the NDVI. What is the reason why we decided to use two different satellites was just to show you what you have to do in the two cases, as the procedure is slightly different if we consider Sentinel-2 or if we consider a Landsat. We wanted to show you how it is possible to deal with the two of them. And therefore, we decided to consider for 2015 Landsat and for 2019 the Sentinel-2. Okay, what we do today, the classification. Classification means that as we are showing you how to do the supervised classification, specifically one supervised classification, in this case, we needed to have some training data. And so we will define the areas that will be used for training our model and for testing the model. And then once we have this data set for training and testing the model, we will train the model for the two periods we are interested in, 2015, 2019. Okay. Then we will evaluate the model that we create, so the classified map. Specifically, we will compute the error matrix. And once we have the error or confusion matrix, we will compute some evaluation metrics. And the evaluation metrics that we are using are the overall accuracy and the kappa. Then the last step is to compute the forest loss and forest gain, computing the difference between the two classified images, masking the forest loss and gain areas, and then computing the total and absolute areas corresponding to forest loss and forest gain. So this is what we want to do now. So first step, preparing the training data, the training and testing data. For preparing the training and testing data, there are more possibilities, as a matter of fact, but we will show you one possible way. And the possible way is to use directly the Google Earth engine for deriving some polygons corresponding to presence of vegetation, so forest, and absence of vegetation, so no forest. In this case, we will show you how to do that, but as this procedure requires some time, because we have to draw the different polygons corresponding to forest and no forest. And then if we want to use the same training and testing data set for the two cases, so 2015, 2019, we have to verify that the selected polygons have the same situation in 2015, 2019. So this is a bit long, requesting time. So we will simply show you, or better Vasil will simply show you how to detect, how to draw one polygon, or one polygon for the forest, one polygon for no forest. And then instead of repeating everything, we will use a data set that we already created. And that we made available for you. Okay, after that, once we have created this data set, we can load these two data sets into the Google Earth Engine platform. So for doing that, we define a variable which is the variable no forest, and we will use this one that is provided by us, and the variable which is the variable forest. And again, we will use this variable provided by us. And here, I don't know if you remember, but here we are also visualizing this data in the part of the Google Earth Engine where there is visible the map we are working on. Okay. At this point, we want to sample the regions that were corresponding to the polygons, to the forest and no forest polygons. And we can do that defining, first of all, which are the bands that we will use for classification. So the bands you see here, we define these variable bands corresponding to the blue, the green, the red, the near infrared, and the NDVI band. Then from that image, we will sample the pixels corresponding, so the points corresponding to the to our polygons, to the no forest and forest polygon. And we start with the no forest polygon, so the points corresponding to the no forest polygon, and we subdivide randomly these points in two subsets, one corresponding to the 80%, which is the subset that we use for training our model, and one corresponding to the 20%, which is the one we use for testing the model. So you see here that we define a train non-forest and a test non-forest, the training data set and the training subset and the testing subset in case of no forest. Then at this point, we can do the same also with respect to forest. So again, exactly everything is exactly the same, and we created the two subsets for training and testing. And finally, once we have these subsets, we put all together the two trainings, forest, no forest, and the two testing, forest, no forest. Okay, now we have the data set for training our model and the data set for testing our model. Okay, let's stop here. By now, I will give the word to Vasil, and Vasil will explain you what to do. Thank you, Vasil. Thank you, Vasil.
Thank you. Thank you. I shared my screen. So I'm starting a little bit back from the first part that I already shared the script with you from the end of the part 1, and now you saw it in the presentation. So you can directly go and follow the code. So what we did the previous time, everything is in the script if you open your Earth Engine. So we have all the introduction. Just for now, it is commented, so it will not be run because we are not interested in it. But if you want to do some of the exercises, just uncomment it. You have to remove the slashes, so it will go and it will be run. Anyway, here is the main part that we are interested now, and everything in the pre-processing steps is already there, and we can run it. Most probably in the beginning you will not see anything because by default all the images, they are off. They're not to the canvas, but you can turn them on and you can see everything. So this is what we did till the previous time. Now we have to start. Actually, I'm just going to work on another one, not to change anything to the saved one. So I prepared everything. Now we have to create a training and training and testing data sets. What we will do those training and testing data sets, we will use them to feed them into our algorithm and to point them. Okay, in this area we have forested areas, and in this area we don't have forested areas. In non-forest area, we will consider everything that is different than forest. It can be also water bodies, some rivers, some areas over cities. So everything that is not river, not forest, will be included in. So we have to define manually those areas. As we already understood, it's a little bit troublesome and it will take time to be done properly. So I'll just show you how it is to be done manually, and I will not make you do it now. We have prepared everything for you. So I'm just loading now the Sentinel 2019 image from the layers panel and turn it on. I zoom to a level that I'm feeling comfortable to work on. And now when it is loaded, I have to create an areas that is going to show our forest and non-forest areas. For that, we can use here the geometric tools. If you want to draw a shape that it's not so regular, you can use the shape tool, or if you prefer to draw more rectangular, you can use rectangle. Doesn't change a lot. So let's take the rectangle, and you see now it is a new layer created. Let's change a bit of its settings that we will know what we're going to do. First thing, what we will do is to change the name. Let's say it will be non-forest in this case. We have to change it as not as geometry, but as a feature collection. So in the feature collections, we will have an attribute table with properties and values, and it is mandatory for us to add some property. In this case, our property will be called land cover. Land cover. And we have to assign some value because we are going to deal with two classes. One is going to be forest and the other one non-forest. It is quite easy to work in a binary way. So just 0 and 1. In this case, we can decide to put 0. Actually, it can be whatever value you prefer, but let's say 0 for now. So we are missing forest cover. We are putting some color that you prefer and we click OK. Now, the next step is to actually draw a polygon onto your map canvas. So we are taking the cursor and start drawing on the area that you want. First click and then you second click to close the whole area. Now you see I have my first polygon in an area that there is obviously no forest cover. To stop, you have to click exit. So otherwise, each time you click on the map canvas, it will start drawing a new polygon. Let's just quickly repeat the process by creating a new forest layer. So we go to the geometry imports and we click new layer. We go again to the settings, edit layer properties, and we call it forest. We change the type to feature collection. Here it is important that when you're putting the property, it should be exactly the same as the previous one for non-forest. So we put again land cover, but it is also important that we change the value. Otherwise, it will be exactly the same. So we want it different, and we're putting 1. Okay, we create, and we are ready to start drawing. Okay. And now we have two polygons that one is representing the forest cover and one is representing the non-forest cover. But as I said, to do this for each year, 2015 or 2019, and we need quite a lot of examples, not just 2. So it will take time and we will not deal with it now. For that reason, we have done already the assets that are ready to use. and we can load them. So I'm taking from the slides. You can also copy and paste from the PDF, and you can see that actually they're already defined in my personal asset that I showed you the previous time how to share. Now we can use them directly from my asset. We're defining them as a feature collection, and we have again no forest and forest. And the second part of the code here is just to add them to the layer, to the map canvas, excuse me. Not to make a mess, I'll briefly delete the what we created manually because the names are the same. Okay, so now we're putting, and we can run again the code, and you can see that our layers are loaded. You can, if we turn off the non-forest, you can see how many forest layers we have added, and also we have the non-forest. Okay, let's continue with the presentation. I'm taking the second part of the script, that is defining the parameters and the spectral bands. Okay, let's see what we have here. So in this variable band Landsat, we are defining a set of bands that we are going to use, because if you remember, in the Landsat, in general, there are more than 4 bands, but we want to use just the RGB and the near infrared. And we are also including the NDVI, which we created in the first part. So then we're defining the sampled non-forest Landsat. So we are taking all the polygons, we're overlaying them over the image of Landsat 2015, only for the bands that we have previously defined, and we sample those regions. Here we sample with non-forest. We're using the property land cover and the resolution, the scale that is the native for Landsat. In this situation, it is 30 meters. Then we're defining a threshold that we want to define, separate both of the data sets into training and testing. One will be used for training and the second part will be used for testing purposes. For that, we're creating a random column with random values between 0 and 1, and we are assigning them that in the case of train non-forest, those values, it should be all the values that are lower than 0.8. And in the case of test non-forest, we are taking the second part, the leftover part of these random values. So everything from 0.8 to 1. Okay, we have to do the same also for the forest part. Let me take. The principle is completely the same. Just we are changing the collection that we're going to use. In this case, we're going to use no forest, and here below we're using forest. Again, the same properties, the same image, the same values. The final part is actually to merge all those sets. So on one side, we're taking the training forest part, and on the other, we're taking the train non-forest. And we will have one cumulative data set, let's say train Landsat, and the same for test Landsat. So I think for now, this is it, and we can continue with the presentation slides.
Okay, so thank you, Vasil, first of all. And then I know that there is a problem with the slides that were not made available. We are trying to solve it right now. When I have the message that the slides are uploaded, I will let you know. Meanwhile, I will go ahead with the presentation. Let us try to go not too fast in such a way that you have the possibility of better following me. Okay. So we are here. And next step is the classification. So now we want to classify, data. I don't know, is this one appearing? We want to classify data, and specifically for classification, we decided, we used different algorithms, as a matter of fact, but the one performing best, sorry, I will remove this one. Sorry for that. I needed to remove this one. Okay, now I can share it again. Okay. So we tried the different algorithms, but in the end we saw that the algorithm performing best was the random forest. And so this is the one we want to propose you. And it is a supervised method that is based on decision trees. It relies on bagging techniques and as a matter of fact, what we are doing is to apply multiple models on the same learning algorithm, which are trained with samples of the original data set. And what is done is, as a matter of fact, to use the ones reducing the variance. So once we have all these trees, we consider a voting procedure, and as a matter of fact, we take for the final vote the result corresponding to the majority, if it is a case of classification like the one we are considering now, or the average in case we are dealing with a regression. This random forest model is good because we have a few parameters to tune. It can be applied both to data which are continuous or categorical data. The only drawback is that it could be computationally slow because we have to create all the trees and to obtain the output for all the trees. But as a matter of fact, at least in a problem like the one we are proposing you, this was the one performing well, the one of the machine learning performing well. And so we decided to propose this one because it is a simple one. Okay, so at this point, for doing that, what we want to do is to train this random forest classifier using our training data set. And once we have trained our classifier with our training data set, what we want is to verify which is the quality of this classification. And therefore, the first part is for training the model. The second part is for obtaining the error matrix or confusion matrix and obtaining the metrics that we need for evaluating the quality of the classification. So the overall accuracy and the kappa. Okay, so once we have the overall accuracy and the kappa, we can also print it, and using this command that we already saw last time, that is possible to print the values we are interested in, and therefore we can check which are the values obtained in our case. Like in this case, we are using the 2015 image we created before. Just to have an idea about the values we are expecting, the closer we are to 1, and the better is the quality of our classification. Therefore, an overall accuracy of this kind is a very good overall accuracy, and also the kappa index that we obtain here, the closer is to 1, the better is, and therefore also in this case the result is a very good one. Okay, so now it's your turn of classifying of training the classifier and obtaining the statistics about the classification.
Okay, thank you. In the meantime, I think by now the PDF should be shared, so I hope you are going to manage to catch up with everything. So after we define...
Sorry, Vasil, as before,
Yes.
people didn't have the PDF. Can you, is not yet. So what we can do is, now you go ahead with the this part, but then when there is the PDF, probably in order to make everyone in a comfortable mood, we will show again the complete code. But okay, let's go ahead, and then please, please, we will show again the procedure in the end. So follow us, and we will do it again another time when the PDF is available.
Okay. Okay. So now to what we reached, we have all the training and testing polygons. So we sampled them, so we have the information of the band values for each for the image of Landsat 2015. And now we have to create the classifier, which will actually use this information to train a model and then actually to predict it on the rest of the images of the image, because now we have just information for some pieces of the image. For this, I'm taking now the classifier part, which is let's say very simple in this way to be defined. Okay, let's a bit separate it to be more visible. Okay, we're defining it as a new variable that is called classifier 2015. This is from the container of classifiers, and random forest, in this case, it is called smile random forest. And if you want to check what else it can be used, you just have to go to the documentation and start typing classifier, and you'll see the other algorithms that you can input and use actually. So we're defining our random forest classifier, and for simplicity, we're just defining it with 10 trees, because firstly, we're working on a big area, and then we want it to be a little bit faster now. Of course, if you increase it, it's possible that also the accuracy and everything will be better, but for now, 10 should work fine. And to train it, we're defining this dictionary that the features are actually the features that we just defined, train Landsat. We're going to use the property for classification land color. So if we go back, so it will use 0 and 1 values. And the properties that actually will be used are the bands that we have previously defined here, RGB and NDVI. We have decided to use those bands, let's say, because they're more sensible to vegetation. So once the classifier is constructed, we can actually evaluate how it will perform. So for this, we're just going to call the confusion matrix. So it will show us all the confusion matrix, how it will perform. So it will classify all the values that we have put in the train after it's learned how to all the weights. And then it will compute the accuracy and the kappa, and everything will be printed in our console. So let's run it. While we're waiting for the values to come up, I want to say 2 additional things. So firstly, we're evaluating our classifier. We're not evaluating an image, we're not testing. So here exactly the values are expected to be a little bit high. Firstly, we have our confusion matrix. So we see that more or less 40 pixels are misclassified. And because of that, we see that the accuracy and the kappa are almost 1. Don't worry that those values can be slightly different from what you received or even what is in the slides. It is normal each time when you run the model, those values to be slightly different, because each time when you run the script from here, it will rerun all the training again. And of course, because it's on a random principle, it can have some variation, therefore some differences. Okay. Then we'll do almost the same thing with the test data set. So we have the second part. So we're taking the classifier and we're actually classifying the whole image. We're selecting the bands that we're interested in, and we're classifying the whole image using the classifier that we just defined here. We can also test to see how the classifier is performing. So we will use the test dataset, which was not used into the training part. So it's some completely new information for the model. So we will see how it will perform. We will do something similar. As before, we will classify the test dataset. We will compute the error matrix. We will print it, and we will compute the accuracy and the kappa. Okay, now we can see here we have the training values that came. No, those are the validations. It can take a little bit more time. If it's getting a little bit slow for you, better to turn off or from the code to make all those layers that are loading, to make them by default 0, so they don't turn on. Here it is strange why everything is 0. Okay, theoretically should be everything fine, but probably we can continue with the slides and I'll see where the mistake came, and I'll come back with you in a bit.
Okay, so thank you, Vasil. And I'm still waiting the slides to be uploaded. As soon as they are uploaded, I will let you know. And again, don't worry about that, because in the end, we will summarize again once we have all the slides, and therefore we can copy and paste all the code. We will comment shortly again for you in such a way that you can better follow us. Okay, so let's start again with the presentation. Now we have created the classifier, and we have classified the data. We have used this mechanism of training the data with a subset, and testing the data with another part of the same set, but without using, obviously, the data we used for training. So taking our data set, subdividing randomly in 80% that we used for the training and 20% that we use only for the testing. And those were the results that Vasil was showing you. At this point, we want to do something more, because besides that, we decided to use also an external data set. So a data set derived in a completely different way, completely independent of the training and testing data set that we used before, and with a better resolution. Okay, so this is the data set representing for us the ground truth. So as a matter of fact, we are dealing with our images and then with three data sets. One that is used for training the model, and therefore we can check the model fit. So what is how the model is trained using the training set. Then we can verify the model test. So we can test the how the model is able to predict our data, and we do that using the testing set. And then we can use also this external validation, external data set for validating our model, for doing the model validation. The mechanism that we use in any case is always the confusion matrix, and we compute the overall accuracy and the kappa, but obviously what we obtain in the case of the external data set is slightly different, and it is like comparing with the ground truth for evaluating, for doing the validation of our model. Okay, so the data set we are using, as I told you, is a higher resolution data set, and it is something that was obtained with photo interpretation. And it is something that we make available to you, and it is something that we recommend you to obtain or in the field, or being sure that these corresponds to a better quality data set, exactly because we want to validate our model. Okay, for instance, in this case, we obtained starting from images that are higher resolution with respect to the images that are used for classification. Okay, so using this data set, we do exactly like we did before in the case of the testing, but we know that the meaning now is different because it's an external data set, completely independent of what we used, and therefore the result that we get, which can be considered the validation as the value for validating our model, is slightly different with respect to what we found before. Okay, therefore we are using this reference point for validating the model, computing again the error matrix as we did before, computing the accuracy, compute the overall accuracy, computing the kappa, and you see that the result that we get in this case, it's a bit lower with respect to what we found before, that as it is expected. Okay, so at this point, anyway, the result is good because you see that the overall accuracy is 93%, the kappa is 87%. So the result is good. So we can say that the classification is good. And at this point, we have the final classified map, and we can add our final classified map to the where we have the all the maps and images into the window of Google Earth Engine. Okay, so now we have our map where the red is the non-forest and the green is the forest. I believe that now it's time to start doing that part. And meanwhile, I believe that you have the
I think, yes, in the
code
meantime,
available.
that the PDF should be in the comments shared. Also, I found a mistake, so the PDF will be updated eventually. To everyone that is wondering what is the problem here, why we had 00, It is because when we're creating the test Landsat dataset, we're merging it with the non-forest with the non-forest. So basically, we don't have a forest dataset depicting one. So we just have to delete none. So it will be test forest Landsat merged together with the test non-forest Landsat dataset. If we run now, we will see, we will receive this time the confusion matrix and the accuracies. Okay. Okay, we got them. Of course, naturally, they're a little bit lower than the trained model.
Vasil, sorry,
yes.
may I ask you before going ahead, as now probably everyone has the slides available because they were shared, if you can go back to the beginning of the code that was added today in such a way that everyone can check and verify and try to repeat. So just a bit quicker than before, but going back again and showing the different steps.
Okay, yes, definitely. So if we start from the slides, the first part, what we did was actually to add the polygons that we have created for you. That they're called the variables snow, forest, and forest, and they're actually feature collections directly from my personal asset space. Here it can be a bit different because I just put those layers to be by default off. So if you want to visualize them, either do it from the layer manager or just put them from here. No, actually here it is wrong. It should be here below. Sorry, I made a mess now. Okay, so here we're adding the layers to the canvas. In these first two, we're just loading them. In the second part, we are defining the list of bands that we're going to use for our sampling and for our classification. Bands Landsat, it means that we're going to use the blue, the green, the red, the near infrared, and the NDVI as a band. NDVI, of course, it is already done, added as a band in the previous part. Then we're doing the sampling part. So we're using the Landsat 2015 image for the bands that we have defined. We're using the data set of no forest polygons with their property of land cover and with the pixel resolution representing the native one of Landsat 2015, so 30 meters. So we are taking the information for each point, for each pixel, and then we're defining a threshold for how we will separate the whole data set into train and test. You can change this if you prefer, but usually the ratio is 70-30, 80-20, something like this. We're doing the both separation here in these two parts, and we're doing the same thing, just this time we're using the forest polygons, not the non-forest, and it is completely the same. Then we're merging both training and both testing datasets. So please pay attention now when you're copying and pasting. When we're defining train Landsat, it is okay to copy and paste it from the slides. In test Landsat, just change please these to test forest Landsat to be merged with test non-forest. It is now test non-forest merged with test non-forest. Okay. Then we're creating the classifier for 2015, in this case, a random forest with 10 trees. And we're using as features the previously defined train dataset of Landsat with the properties of land cover and the list of bands that we have defined. We're computing the confusion matrix, the accuracy, and the kappa. So this is just printing and computing. We're actually classifying the whole image. We'll see in a bit. And we are doing the test dataset, evaluating the test dataset. So I believe from now we can continue all together. I hope we're together. And now let's include the external data set that we have. So again, we have a data set that was externally made using high resolution images, and those points that we have added, they are not in the polygons, they haven't been used till now, so we will just use them to externally validate our image. Let's see them. Okay, those are the polygons. No, sorry, I copied and pasted the wrong part again. We need the reference points. So the reference points are the ones that we have defined before. Okay. As you can see, we're calling the reference points from my asset, and we're filtering them because they also have a property, land cover. Just this time it is a little bit slightly different with underscore, but the values are again like this. 0 and 1 for non-forest and forest. So we're just separating, applying filter. Here we're calling the values that are equal to 0 are the non-forest. Let's see them. Okay. Okay. We can actually evaluate the performance of our classifier according to those points. So I'm going to the next slide, external validation. And we're first converting all the points that we have as a geometries now, and we're taking their properties, the values that we have previously manually defined 0 and 1. And we're sampling the classified image. So the image that we classified here, we're sampling it with the same points. The sampling procedure is the same as before, just this time we're using reference points. And we're evaluating in the same manner. We're creating the error matrix with land cover and classification as two values, and their accuracy and kappa coefficient. Let's run. So firstly, here we printed the feature collection that is loading. So we have 1019 points. We can see the error matrix, and here are our accuracies and kappa coefficients that we have computed for them. Okay, so we actually used our classification image, but we don't see it. So let's add it to the map also. Firstly, okay, we're defining a palette for defining some colors. Red will represent no forest, and green will represent the forest land cover. You can, if you prefer, you can define it directly here or use it just as a variable. So we are adding to the layer the classified 2015 image with the minimum value is 0 because we know that it's 0, and maximum is 1 because we have just only two classes, the color palette and the name. Let's run and actually see this image, this map, sorry. Okay. Just to repeat, if now, because the process is getting a little bit slower and slower, it is suggested all the previous layers that are added to actually turn them off by default, because they're computed each time and can make the process even slower. So there we have it, the classified image of 2015 with Landsat median image. Okay, I think we can continue with the slides.
Vasil, I was thinking as we are a bit late, if you want to show how to do with Sentinel, because it's exactly the same in such a way that you can repeat again the procedure. They can follow you also, the people who are try now to copy and paste the code. And we arrive to this point also with Sentinel, because the procedure is exactly
the same.
only using Sentinel in such a way that you can repeat again.
Okay. Okay, so I'm copying and pasting. Let me put here a comment that we're working for Sentinel 2 now. And if you go to the next slide, you'll see that actually we put all the code in one slide because basically we're doing exactly the same thing. And let me just copy and paste it in the code editor. Let's go. You can see that it is completely, the structure is the same. The small differences are actually from the properties of the Sentinel. So we have different band names. In this case, they are B2, B3, and so on. We're using those. Again, we're using no forest and forest polygons that we have from before. I'm saying again because they're verified that in 2015-19 they should be corresponding and they're not changing properties through the years. So if you want to do this by yourself, you have to ensure that the forest and non-forest polygons in both years are corresponding and they're correctly. In this case, the other difference is the scale of 10 meters, because this is the resolution of Sentinel. And we can see that we're doing exactly the same, separating the training and testing into 80% and 20. We're sampling the Sentinel 2019 image. And here again, we're combining the train and test. And actually, again, here it is wrong. So please delete the test non-forest Sentinel. So the test Sentinel, it is equal to test forest Sentinel merged with test non-forest Sentinel dataset polygons. Okay, again, because of all the small differences that are the bands, the resolutions, we have to create a new classifier. This time we're calling it Sentinel classifier, but all the settings are the same. So let me just copy the second part. Sorry. The second part of the code that we need. Okay. Okay. We're creating and we're continuing classifying and doing exactly the same. We're testing the training set, the testing data set, we're classifying and we're evaluating the points. The same is that we're adding the classified 2019 to the map canvas. So now when we run everything, we should be able to see it. Okay, it's coming. We can see what are the accuracies. You can see the error matrix. Accuracy, this is for training. Now it is still computing the testing values. And here the external values. You see that actually in 2019, it performed a little bit better than the Landsat 2015 for the external test validation. Okay, so now we have also the second map of 2019, and we can actually just quickly compare and see that there are differences between them. But we will see now how and what we will do. Okay.
Yes, thank you, Vasil. And I want just to add one point, because in this case, we decided to use a unique training data set for both images and the testing data set for both images. So with respect to that, we have to be sure that the situation in those points has not changed in the time. In principle, we can also decide to use training and testing for the image of 2015 and a different training and testing for the image 2019. Was just because in our case, we decided to use a unique that we have the same, but obviously you have to check that the situation in 2015 in those points is the same as the situation in 2019 in the same points. Okay, so let's go ahead with our analysis, and now what we want to do is to compare the two solutions, as a matter of fact. But we saw that there is something we want to improve, and this that we want to improve is related to the fact that if we look at our images, if we look at our, sorry, again, there is one problem in sharing. Okay. If we look at our images, what we see is that there is some noise around in our images. So you see that both for Landsat data, and this is something that you can see also in your Google Earth engine if you
Sorry to interrupt you, but we're seeing your presenter mode, not the full slide.
Yes. Let us check. Let us change it.
Because it is a bit small, sorry.
Yeah. Let's do it this way. Let us see if no. I'm trying to solve the problem. I don't know what happened. Okay, let's do now. Yeah. And I'm not able to change it. I'm not able to change it. I don't know why.
Probably if you go right click and change the mode, it will happen.
I can just change it. No, I can finish. I can. No, because I have this one. No. I have a menu exactly where I can change the mode of my presentation. So.
Okay, if you want, I can share my presentation.
Yes, please do in this way, because this seems to be not solvable. Today is a bit it's a bit hard. Okay, so we can do in this way in any case. So if you look at your Google Earth engine, what you see is that there is some noise, as a matter of fact, in your classification. So you don't see so sharp classification. There are some points where we see these salt pepper effect that obviously it is not realistic. So what we can do in this case is to apply some morphological operator in order to clean a bit our image. There are many different possible morphological operators, but in this case, what we suggest you to apply is this focal mode. Focal mode means that you are dealing with what's happening around every pixel. You are looking what's happening around, and then at this point you will use as operator.
I'd like to address myself to the directors of the three bureaus in this. When dates are chosen, in particular with regard to advisory groups, we would really like to ask
there is somebody
at the same time as the block of council working group meetings. And with regard to Whitstone,
is it possible to switch off the microphone? Okay, thank you. So we are using this focal mode. That means that as operator, we are using the mode. So we look around, we decide a certain dimension for the window of pixels that we consider around every single point. And we look at the mode of the values that we find inside this window. Specifically in the case that we will show you, we decided to consider as sides of this window radius of this circle, the radius equal to 2 pixels, and as operator the mode. So the value that appears most frequently in the this window is the value that is selected as the value for the center, the pixel in the center of the window itself. Okay, so let us apply exactly this kind of operator, morphological operator, in order to clean our data and obtaining the cleaned data. And then at this point, and you see here what you have to use for cleaning the data and for obtaining the cleaned map. And then if we go ahead, I suggest Vasil to go ahead. Then if we go ahead at this point, we apply it and we obtain the cleaned map.
Okay, probably we can just explore together what we're a little bit more in details, let's say. When we browse around the map, we can notice that here and there are some pixels that, okay, if really they're just a big cluster, most probably the area is correctly classified. But if there is 1 or 2 pixels that are among a very large group of the other class, most probably it is wrong. So we're talking about something like what we are seeing here on the screen. So let's add the piece of code that is applying the focal mode. You see that we're defining new variables as on the classification of 2015 and 2019 with the focal mode of a radius of 2. And we're adding them again to the canvas. Let's run. Okay, just I'll show you the example of 2019. Okay. This loading. Okay, probably we can go again to the same area to see what is happening. Of course, the value that we selected, it is not strictly defined. So in your case, another value can work better, or even for this case, it's not the optimal, but you can see that it cleaned a bit and regulated more the classification. So I think for this part, this is it. Probably we can continue actually with the resampling. Okay.
Yes. So at this point, we need to do 2 more steps. So first of all, we have to keep in mind that we are dealing with two different images, and one is at the resolution of 30 meters, which is Landsat 8. On the opposite, the second one is at the resolution of 10 meters. And therefore, we need to resample in such a way to have the same resolution. Okay, and so we decided to have the resolution of 10 meters for both of them, which means that we are not improving, obviously, the resolution of Landsat. Simply, instead of 1 pixel of 30 by 30 meters, we are considering 9 pixels of 10 by 10 meters with exactly with the same value. Okay, so now at this point, once we, if we wanted to resample, we will use this function that you see here, the resample, and using the bicubic operator for resampling. And then the other point is that we wanted to reproject our map in such a way to be given in projected coordinates. In the beginning, I want to recall you that we had the data in WGS84. Now we are reprojecting in UTM, the specific UTM of this zone, so reprojected coordinate. And therefore, with these steps, we can both reproject and resample our data. Okay, now the resolution of both the data is 10 meters. Vasil, I believe that we can go ahead in such a way to finish the slides, and then you will show. What you think? Okay, because now we have the next step is to save the data, and for saving the data, you see we export them as assets, and then at this point we have our data saved. Next step, we load them back on the Google Earth engine as we are able of as we needed to do for every external data set, and we added the classification maps to our canvas. Okay, so now we have again our two maps, and we can compute the map difference. Computing the map difference, you see, simply we define this new variable given by the one map minus the second one, and then we can add it to our canvas, and that's okay. Last step is computing the forest loss and gain in this period. Now we have everything, and therefore next one. Okay, now we have everything. We have that 1 is forest, 0 is non-forest, and therefore we can obtain the map corresponding to the forest loss and the forest gain, giving the color we want to these two value, and then computing also which is the area corresponding to the forest loss and the forest gain. And this concludes our exercise. Okay, Vasil, I believe that you can show them how to do that. And sorry for being a bit late, but we had some technical problems.
Sorry, I couldn't. Okay, I'm back to the presentation, to the share. Okay, so we reached to the focal mode. Let's go back a bit to the slides, and we need to do the resampling. I'm taking again the piece of code that is for the resampling, and I'm posting it. What we are doing here again is forcing now Earth Engine to work at this scale at 10 meters per pixel. especially for those, because Earth Engine, it is working on a pyramid scheme. So also, if you notice, each time when I zoom out, you zoom in, and it is recomputing everything from the beginning at the scale that is finding now. So for this area that we're working on, almost 50,000 square kilometers, to force Earth Engine to work at 10 meters, it will be really even it will be computationally intensive also for the platform. So that's why for now you don't see that we're adding those maps at 10 meters to the canvas. So just when we run, we are going to print the output resolution. So how we're doing that after we apply the resampling and reprojecting of the image, we're calling its nominal scale by using projection and nominal scale functions. So in the end, you see the output, it is 10 meters for both of them. I'm again repeating, what you see here on the canvas are not the images at 10 meters. So that's why also it was in the slide, this intermediary safe step. It is not actually necessary to do it if you're working in some really small area. Most probably the engine can handle and compute everything at once. But if you're working on an area similar to this one or even bigger, I think it is better to export at least the classification maps till now, because it is possible that you will not be able to continue with your processing. So in the previous part, we were talking about how to export image or assets, and now we're going to use, I think, for the first time, and we're going to export directly to our assets. If you go to documentation, you can see export, and you'll see the options that you have to export. You can export an image, a table, a map, or to the asset, to G Drive, or to Google Cloud Storage, and you can see all the parameters that you need. Here, this probably it is better to change it now. Okay, not now, but it is better to change it because it's just some generic name that I put to remind you that if you want to put it in some specific asset folder, you have to specify it here. You have to define the scale and the reference system that we are working on, and for which region we are defining. And that's it. I'm not going, I'll just show you when you run what is happening, but of course I'm not going to export it now because it will take some time. Let me turn off everything again. You see when it reaches these steps to export, now it will appear here as a new task. We haven't seen this till now, so when you're exporting something, here the task tab will highlight and will beep that you have something waiting for your attention. You can hit run. It will not start immediately. Basically, the form that you filled here, it is filled. It is the one that you did in the code. So that's why also the link here, the string, it is like this, but you can change it as you prefer. And when you're ready with your settings, that you just click run, and it will take some time. So I will not do that because it will take time. For that reason, I have already done it and exported it. And that's why, again, I'm sharing with you the ready product. So you can just load it as an image from my asset, and we can load it. Okay. We can actually also visualize it in the end. Okay, we are adding the classification from that is already computed. So now probably you'll notice that everything is loading much faster. Should be. No, because it is doing a lot of other computations till it reaches this point, but the loading of the maps is much faster. And if you want, you can explore it and everything will be much faster. Otherwise, each time when you zoom in, zoom out, it will compute at a new. So now we are ready to actually continue and to compute the difference between those two maps, because we are noticing some difference, but we actually don't have a map with it. So I'm creating a new variable difference, or diff in this case, for which from the map of 2015, the classified map, I'm subtracting the classified map of 2019. And I'm adding it to the canvas. You can see that a bit here, the parameters are a bit different, the visualization parameters, because in this time we will have three values. We have, by the classification, we have 2, 0 and 1. But when we do their difference, we can also have a third class that is going to be -1. And in this case, we will actually depict forest gain, because if in 2015 we had 0, so no forest lost. In 2019 we have 1 forest. The difference is -1, which is actually forest gain. And we're defining those values and the colors that they're going to represent. Blue for gain, no, green for gain, blue for no change, and red for loss. Let's see what is the difference. Okay, it should come. Okay, so you see highlighted now all the difference that we have. I'm reminding, green is the no change pixel, red is the forest loss, and blue is the forest gain. But what else we can do? We can actually separate them, just because we are not interested into the no change layer, let's say, for now. So we can apply a mask, and for that we can define two new variables. Forest loss, for which we are using the difference layer, and we're updating it with a mask that is the difference layer equal just to 1. So we want all the pixels that are equal to 1, and they will be added to the map canvas as forest loss in red. And the same we will do with the forest gain, but just this time we will take all the values equal to -1, and we will put them in green. Okay, probably I can turn a bit of layers to be faster. You see that also task is loading, so it is better to, we can put as a background, let's say as a base map Sentinel 2019. So we have it. We clearly defined the areas that are affected by severe deforestation, and actually those that have recovered. And we can compute also those areas. If we continue with the slides, what is happening here? We are okay, we have already computed the area of interest, so probably we are not interested in it now. But we want to compute the area loss. So we are taking the forest loss variable that we have created before, and we're multiplying by a special image, a little bit more different image. We are creating an image that each pixel is equal, has the value of its area. So for this image, forest loss, we will create a second image, and each value of the pixel will be their area, and we will divide it by to convert it in kilometers. For that, after that, we have to sum all those pixels to take to compute the total area of interest. So computation of raster area raster in Earth Engine is not really the straightforward one, but it is done in this way, and we do the same also for the forest gain. Just the difference is this time that we're dividing by minus, because actually the value that we had for minus was -1, so just to have positive value. And we have relative losses and gains we're computing below. So let's run and compute all those values. Okay, we don't need this one now. Okay. Probably again, it is possible that the values you see here will be a little bit different than what is in the slides and what you obtain. And this is again due to the nature of the algorithm classification that we're using. So it can be a little bit of small discrepancies. And we have it. We computed the area that has been lost due to some reason, and the area that has been recovered. And the last part is actually to export. If you want to export to drive, to G drive, let's show you how it is done. We can export just the forest lost and the forest gain segments. Pretty straightforward and similar to what we saw before. You define the parameters. Just this time we're using image to drive, and when you run it, you have again two new more tasks in the tasks bar that will come in a bit. And okay, you see each time the more you do with Earth Engine, it's getting a little bit slower and slower. So it's good to keep it clean, and we have it. If you decide to export it, the same procedure, fill the blanks if they're not filled, and click run, and that's it. Okay, I think this is it from me. Thank you. I hope it was clear and useful.
Thank you, Vasil. Yes, it was clear. Unfortunately, we had some technical problems before because there were not the slides uploaded, and therefore in the beginning people had some problems, and then okay, but this is normal. This happens during when we are not performing, but really doing our activity. So I want to thank you a lot, Vasil, for this very, very good presentation, excellent presentation. I want to thank you also all the assistants here who are still answering to questions. I see that there are still questions going ahead. And I want to thank you, to thank also the attendees. What you can do is if you compute the deforestation in other parts of the world, you can share with us your results, because we are curious about the fact that you are using what we taught you, and we are curious about seeing the results. So if you want to share with us what you are computing, reusing this webinar, we will be very happy about that. And again, at this point, I want to thank the people of ITU. I want to thank Vasil, and I want to thank also my students, the students of the Politecnico di Milano, so Juan Francisco Amieva, Alessandro Austoni, Martina Esposito, Ahmed Abdal Ghaffar, Giulia Leonardi, Ahmed Mohammed, and Nicolina Zaleni. Thank you so much to you all, and see you for the next webinar sooner or later. Ciao, ciao, ciao.
Thank you, bye.
We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.